Hi everyone, my name is Wei Chun and I'm here to present my topic on SOJA, which stands for Swap-Based Outer Join Algorithm for Parallel Outer Join. Without further ado, let's step into the introduction and background. My research domain is on parallel join optimization for MPI on HPC. In this case, MPI is one of the common communication protocol deployed on high-performance computing clusters. It is also without a doubt that modern data analysis rely heavily on joins between large datasets in order to relate information between two distinct datasets. However, joins are expensive due to the amount of communication that has to be involved between processes in a distributed environment. The authors of this article realized this problem and produced a novel algorithm that is able to minimize memory usage while maintaining equal or better performance compared to its industrial counterparts. I chose this topic because I believe that it has huge potential to redefine performance and scalability of distributed joins. Currently, there are quite limited research on parallel joins in traditional HPC using MPI protocols, as most of the studies are done on popular distributed processing frameworks such as Spark or Flink. Additionally, existing approaches rely heavily on redistribution or broadcast, which leads to common problems such as data skewness, where one of the processes has much more data to process compared to others, and data duplication, where data is duplicated multiple times over multiple processes. Both of these problems will lead to slower performance due to more disk swap between the memory and the disk, which involve expensive I/O operations. Now, given that, the author produces a hypothesis such that the SOJA algorithm could have a significant reduction in memory usage by minimizing communication costs between distributed processes and by reducing the local join costs. The authors aim to achieve this by replacing the redistribution and or broadcast with a swap-based approach by having the smaller tables swap between processes using a ring topology. Using this method, we will be able to mitigate data skew and duplication by ensuring that each process in the distributed environment see the same amount of unseen data. Now, the article aims to contribute three contributions to the big data domain, particularly in the parallel join operations. So firstly, it aims to significantly reduce the memory requirements. Secondly, to maintain comparable or better performance in the worst case scenario. And thirdly, the article also proposes further optimization steps to reduce additional joins, filters, or redistribution that is currently in place or used in current implementation of parallel outer join algorithms. Let's also take a look at some of the related works that are currently implemented, such as ROJA, DOJA, DER, and DDR. For ROJA, it works by first redistributing both tables and then performing a local outer join and output the result in each of the processes. For DOJA, it will first broadcast table R. In this case, table R will be the smaller table between both of the tables. It will perform a local inner join on each of the processes and output the interim results. After that, it will redistribute the original table R and the interim result on each of the processes and perform a local outer join. For DER, similarly, it will first broadcast table R and perform a local outer join on each of the processes. Now, this is the novel thing that is implemented by DER, where it will keep track of IDs of the non-matching tuples. In this case, in step 3, it will redistribute the IDs of the non-matching tuples to each of the processes, and then filter the IDs which appear n number of times where n is the number of processes in the distributed environment. This tells us which of the tuples are dangling. It will then perform a local inner join between the dangling IDs and the original table R and output the results. Similarly, for DDR, it is quite similar to DER, where you first broadcast table R and local outer join and perform a local outer join on each of the processes. However, instead of keeping track of the IDs, DDR actually keep tracks of the non-matching tuples instead. It does this because it wants to avoid the additional join in order to additional join between the IDs and the original table R. So similarly, it will filter for the dangling tuples which appear n number of times and directly output the results. Now, after analyzing on all of these four algorithms, we realize that there are still research gaps on two of the factors, which are namely the communication costs and local execution costs, which could be further optimized. In terms of communication costs, we can see that SOJA is actually the highest due to the amount of redistribution of data that it has to do on step 1. For DOJA, it's highly impacted by the selectivity ratio, where if the number of joint results is high, then the amount of data that it has to communicate between the processes in each of the steps will be quite high also. Similarly, for DOJA, DER, and DDR, these three algorithms are heavily impacted by imbalanced workload, where if the data are not properly distributed, then the amount of communication that has to happen in order to share the data across each of the processes will be high, leading to high communication costs. In terms of local execution, SOJA is still the highest due to the amount of data skew that it could potentially have. For DOJA rely heavily on joint ratio and skewness degree. So if the joint ratio and the skewness degree is high, then the amount of processing that has to be done on each processor will be high, leading to lower performance. For DER and DDR, both of these algorithms have additional filter and join steps, which leads to higher complexity and more processing that has to be done for each piece of data. Now, let's talk about how SOJA aims to solve all of these problems. But before that, I wanted to introduce two of the main concepts that is used in SOJA, which is the ring topology, where each of the processes is joined together in a loop. As you can see on the right-hand side diagram, if first process is connected to 2, 2 connected to 3, 3 to 4, and finally the last one with the first one, 4 to 1. Another concept that is used in SOJA is local hash join, where we will hash one of the table and perform a lookup on another table. Here's an overview of the architecture of the SOJA algorithm that we have been talking about. As a prerequisite to this algorithm, the data or table that are involved in the parallel outer join operation has to be placed in a balanced manner across each processor. Now let's take a look at what is happening on each iteration. During the initial data placement, let's assume it's round robin. We'll be creating a hash table on the larger table S on each processor. We'll then execute a local hash join by looping over table Ri on each processor and performing a lookup on the hash table. We'll also be marking the dangling tuples, which are tuples with no join matches in each table R in each processor. We will then return the intermediate join result as direct outputs. This is done because the interim join results are no longer used in the algorithm, and that we want to be able to keep the memory usage down low. Each processor will then send the marked table Ri to the next processor according to the ring topology. Note that the last processor will wrap around and send it to the first processor. The whole process will be repeated n-1 time, where n is the number of processors. On the final iteration, we will then output the marked tuples in table Ri as dangling tuples. That is what is happening on the SOJA algorithm in terms of operations. Now let's take a look why this architecture is justified. This architecture optimizes the network communication by restricting it to smaller table broadcasts. It also eliminates unnecessary steps that we've seen in earlier related work, such as redistribution, additional filters, and additional joins. Secondly, it reduces the need for temporary memory by outputting results in each iteration. Thirdly, it avoids table duplication and dangling data storage through the use of table marking approach, similar to what is happening on DER and DDR. Now, given that we already explored the architecture, the authors of the article also done several benchmark tests to test the performance of their algorithm. In terms of the size of the table, as the size of the left table increases, we can see that the performance decrease is least significant, and that the memory usage remains steady throughout and has a significant advantage over other algorithms. SOJA in this case is the red line that we see on the bottom of both charts. In terms of selectivity ratio, we can see that as the table selectivity ratio increases, all algorithms has an upward trend, with SOJA performing the best. Memory usage also remains consistently low as the results are not kept in memory throughout. In terms of data skewness, we can see that as data skewness increases, the performance is not impacted and the memory usage remains constant and low for the SOJA algorithm. This is because the SOJA algorithm has a prerequisite that the data has to be placed in a balanced manner across each processor, and that it's not really impacted by data skewness since it's defined on the join key, since data skewness is defined on a join key, which the ring topology had already helped to elevate. Now let's take a look at what let's compare the observation that we have against the hypothesis that is presented earlier. SOJA managed to achieve the hypothesis set prior to the experiment by leveraging swaps. It is able to outperform existing algorithms significantly in terms of memory usage, as what we have discussed earlier in the results analysis. It is also able to keep an equal or better performance in terms of execution time. Now that's about it for the section on SOJA algorithm. Now I'll move on to the next section where we'll look at the proof of concept that I have developed for the SOJA algorithm. So here's the code implementation for the POC of the SOJA algorithm. If you open the SOJA, the zip file that's included in the submission assignment, you can find the similar structure here. And for this demo purpose, I will focus on the soja.py file. So I'll skip over some trivial functions such as hashing an element, creating a hash table, and lookup, and instead focus on the function that makes up the core of the SOJA algorithm. So first, I would like to talk about the process function, which performs the join operation between table R and table S, where table S is actually in the format of a hash table. So this function is the core part of SOJA, which is performing the parallel join and also keeps track of the marking of the dangling tuples after each iteration. So what this does is that it iterates through the R table and look up the element if it exists in the hash table, which is made from table S, right? So if it exists, it will add the matches into the results list and also remove the ID of the current row from the dangling tuples. So this is to avoid us, this is for us to keep track of what is not matched and what is matched in terms of rows in the tables. Finally, we return the results and the updated dangling tuple set. Next is the round robin partition. So ideally, this is not part of the core SOJA algorithm, but for the purpose of this proof of concept, our input data is a CSV file, so it's necessary for us to partition the data into a balanced manner for each processor to process. So this is quite a straightforward function that initialize multiple lists according to the number of processors and then iterate through the data and modulo it by the number of processors to get the index bin which it's supposed to be belong to and append it to that index list, right? Next is the worker function. So you can think of the worker function as what is running on the process itself. So this worker function performs the iterative processing of the data in the process. So it takes in an input queue, which represents the queue where data is coming in from. Next queue, which is the queue of the I+1 worker or the I+1 processor. This is so that the current processor will be able to move the R table into the next processor's queue, right? The next one is the max iteration so that we know what is the last iteration for us to stop. And the output file path is for us to write the temporary data and dangling results too. So first we initialize some variables and then also create the CSV writer for us to write the temporary data. Then we initialize a while loop and call input queue.get where the get function is actually blocking so that this function here is actually polling the input queue to get the input data, which is the R table, S hash table, and the dangling tuples. Then next we will check if the S table is not created yet. So this means that this is the first iteration. Then we will create the hash table for table S. Next, we will check if the current iteration is the last iteration. That will mean that we will want to output the dangling tuples that have been kept track all this while, right? So we will look through all the dangling tuples and then write it to the CSV file. Lastly, if it's not the max iteration, then we'll process the current R table, the S hash table, and the current dangling tuples. So what it returns is the results of the inner join result from the R and S table, and also the updated dangling tuples. We'll then write the inner join result to the file for the current iteration here, and also put the current R into the next processes queue and also put the updated dangling tuples, right? Then after that, we increase the iteration, and this will keep looping until we reach n-1 iteration. Next is the SOJA function, which is the wrapper function around the worker for us to initialize all the queues and processes. So this will first call the round robin partition for us to partition the CSV data equally. As I said, this is only used for demo purposes, as in the ideal world, data had already been partitioned. Next, we will start the timer and memory profiler for us to benchmark the performance of the SOJA algorithm. Next, we will create queues for communication between workers. So we will use the multiprocessing library and create queues so that we can communicate between multiple workers or multiple processes and to transfer information between them. So here we will clear the output file path in case it already exists. Next, we will initialize the worker process with the input and next queue. So we will use the process function, give it a target function, which is the worker function that we described earlier, and pass in some argument, which is the current queue, the next queue, the queue of the next processor, how many processors there are, and the output file path. All of these will be appended into the process list so that we can start it later in a blocking manner so that it doesn't end quickly. After that, we will initialize each worker queue so before this, we already initialized the queue, but then we haven't initialized the data inside the queue. So for this, we'll enumerate for each queue. We'll add in the partitions according to the processor number, and also the dangling tuples according to the number of data in the current partition. After that, we'll call p.join for each processor so that we'll wait for all processes to finish before we calculate the elapsed time and the total memory that is used in the whole SOJA algorithm. Next is the read CSV, which is just a helper function for us to read data from a CSV file. And here is the main argument, main function that we can pass in certain arguments for us to run the SOJA algorithm. So for instance, in this case, I can just say Python soja.py, pass in the R file, which reference benchmark source movie.csv, which I had already included some source data, and also the S file, which is ratings _ 1 million.csv, pass in the concurrency count of 8, which represent the number of CPU in my current computer, and I click enter. You see, after a while, you start processing and output the result of the parallel outer join between movies and ratings into output-soja.csv. You also can see the memory usage and execution time here. Next, let's take a look at some of the benchmark test results that I have run against comparing ROJA and SOJA. To run the benchmark test, you can run make benchmark that will actually run the commands here. However, for the sake of this demonstration, I won't be running the benchmark test since it's going to take quite some time. Instead, I'm going to show you the benchmark run result from previous run that I did, and also some visualization based on the results over here. So in order to view the benchmark test result, I'm going to first initialize a virtual environment and activating it. After that, I'm going to install some of the requirements such as matplotlib that is required to view the visualization. So if you look at the benchmark folder, you'll notice that in the sampling folder, there are codes in order for us to generate dataset with varying selectivity ratio and to generate different sizes. And the corresponding dataset that I generated are stored in selectivity and size separately. Source folder contain all the original dataset that I have used to sample the data according to sampling, the sampling code that I've initialized here. And benchmark.py is just a function, a file for me to run the benchmark test according to the table sizes and selectivity ratio for both algorithms. All right, so since the installation runs on successfully, we can go to cd graphs and run Python visualization.py. All right, in terms of execution times against left table R size, Overall, ROJA has a higher execution time due to the amount of redistribution it had to do on both tables, while SOJA already had its data partitioned equally. As the size of the table R increases, we can see an increasing trend in ROJA, but a constant trend in SOJA. This constant trend could be due to the size of table being not large enough due to the hardware limitation when I was running the benchmark test. In terms of memory usage against table R size, overall we can see an increasing trend in ROJA as it has to keep the interim result in memory. While for SOJA, it's quite consistent or constant, since its output it results to the file on each iteration, hence not much memory is needed over here. For selectivity ratio, both algo have quite constant execution time, with ROJA having a higher overall. This is explained again due to the data skewness problem faced by ROJA. As the selectivity ratio increases, we can see there's no meaningful trend that we can observe, again, which may be due to the hardware limitation on data set sizes when I was running the benchmark test on my local computer. For memory usage, however, we can see that SOJA actually triumphs ROJA as again, it outputs the interim result and ROJA keeps it in memory. So as the selectivity ratio increases, the amount of data that ROJA has to process and keep into memory increases, while for SOJA, it doesn't have to process as much memory or process as much data or keep as much data in its memory. In terms of data skewness, we didn't actually run a benchmark test since SOJA is not impacted by the factor. And overall, for the whole benchmark test, most of the result that we see in the test correlates with what is expected in the slides earlier in terms of trend. Hence, I would consider that this proof of concept is a successful one. That's it for the benchmark test.